Hey everyone, and welcome. Today, we're going to dive into the awesome world of geometric constructions. We're going to go from drawing simple lines all the way to creating some pretty complex designs, and we'll do it all with just a couple of simple tools. Let's get right into it. So, you've been there, right? You're trying to set up a tent, and it just ends up looking sad and wobbly. Getting that perfect, stable shape is way harder than it looks, because you need to find the exact spot for the top. Well, that's where geometry comes in. This isn't just a school subject, it's the secret to making things that actually work and don't fall over. To get that kind of precision, you really only need two basic tools: a straight edge, which is just a ruler without markings, and a compass. But, and this is the secret weapon, you absolutely need a super sharp pencil. Seriously, a dull point can mess up your entire drawing. Oh, and here's a pro tip. Use a light pencil for all your guidelines and a darker one for the final shape. It keeps everything looking super clean. Okay, so before we can build those complex triangles, we have to master the fundamentals. Think of these next three constructions as, like, the building blocks of all geometry. Once you know how to do these, you can pretty much build anything. First up, how to cut an angle perfectly in half. It's a really simple three-step process. So you put your compass point right on the corner of the angle, at B, and you just swing an arc that crosses both lines. Then, from those two new points, you swing two more arcs that cross over each other. And finally, you just draw a straight line from the corner through that intersection point. Boom, angle bisected. But hold on a second. This is where we go from just drawing to actually doing math. It looks right, sure, but how do we know it's perfect? How can we prove that we've split that angle into two exactly equal halves? What's the geometric secret going on here? And the secret is actually super elegant. It's all about congruent triangles. See, if you connect the dots, you've actually created two hidden triangles. And because of how we drew our arcs, we know all three sides of the first triangle are equal to all three sides of the second one. That's the side-side-side, or SSS rule. It means the triangles are identical twins. And if the triangles are identical, then their angles have to be identical too. It's perfect, and we've proved it. All right, fundamental number 2, the perpendicular bisector. Our goal here is to slice a line segment right down the middle at a perfect 90-degree angle. It's pretty straightforward. You go to each endpoint of the line and draw a big arc. Now, the key thing to remember is your compass has to be open to more than half the line's length. Then you just connect the 2 points where those arcs cross, and that new line is your perfect perpendicular bisector. And you know what's coming next, right? We have to ask why. What's the proof? How are we so sure that line isn't just a little bit off-center, or that the angle isn't 89.9 degrees? What's the geometric guarantee this time? So this one is really cool because the proof is actually a two-step process. First, just like before, we use the SSS rule to prove that those two big triangles we made are congruent. That tells us that the angles at the top are equal. Then we use that information to prove the two smaller triangles are congruent using the side angle side rule. And that second proof is what confirms it all, that the line is split in half and the angle is exactly 90 degrees. One proof unlocks the next. Okay, our third and final building block is making a 60-degree angle, and this one is so slick and simple. You start with a line, pick a point, and swing an arc. Then, and this is the most important part, without changing your compass setting, you move the point to where the arc hit the line and swing another arc. You draw a line from your starting point through where those arcs cross, and that's it. You've made a perfect 60-degree angle. It almost feels like a magic trick, doesn't it? It seems way too easy. But you know, in geometry, there's no magic, just logic. So what is it about that one simple move, keeping the radius the same, that creates such a specific, important angle every single time? Well, the secret is that you weren't just drawing arcs, you were secretly building a perfect equilateral triangle. Think about it. Because you never change the compass, the distance between every pair of points is exactly the same. And what do you call a triangle with 3 equal sides? An equilateral triangle. And what's the one thing we know for sure about them? All of their angles are always 60 degrees. So simple, but so powerful. All right, we've got our 3 core moves down: the angle bisector, the perpendicular bisector, and the 60-degree angle. Now it's time to put them together and start solving the kind of complex problems you're going to see on your tests. So let's check out this challenge. We're asked to build a specific triangle. We know the length of the base, we know one of the angles, but then we get this weird piece of info. The sum of the other two sides is 13 centimeters. The trick is, we don't know where that top point A is supposed to go. How in the world do we find it? The solution is actually a really clever mashup of our basic skills. Let's walk through it. First, we just draw what we know, the 7 centimeter base and the 75-degree angle. Then we measure out that full 13 centimeter sum along the top line. Now, here comes the genius move. We connect the endpoints, and then we construct the perpendicular bisector of that new line. Why? Well, remember, any point on a perpendicular bisector is the exact same distance from both ends of the line it's bisecting. So the spot where our bisector crosses that 13 centimeter line is our magic point A. It's the one place where the distances work out perfectly to solve the puzzle.
Okay, you ready for the final boss of triangle construction? This is what you do when instead of the sum of two sides, you're given the difference between them. The logic is similar, but there's one tricky detail you have to watch out for. This slide lays it all out. It all boils down to which of the two sides is the longer one. If the side connected to the angle you're given is longer, you mark the difference along the main line, just like you'd expect. But if the other side is the longer one, you have to extend your angle's line downwards in the opposite direction and mark the difference there. That is the one key difference you gotta remember. Let's quickly run through an example for that first case. We draw our base and our 45-degree angle. Now, this time, we mark the difference, 3.5 centimeters, along that angled line. Then we connect the dots, just like before. And what's our key move? You guessed it. We construct the perpendicular bisector. The place where that bisector hits our main angled line is our final vertex, A. It's the same logic, just applied in a slightly different way. Okay, we have covered the hows and the whys, so let's wrap this up with some super practical, rapid-fire tips to make sure you absolutely nail these questions every single time. First, let's talk about what not to do. Using a blunt pencil is your #1 enemy. It kills your precision. The other huge one, erasing your construction arcs. Don't do it. Those arcs are your proof. They show how you got your answer. And please, please, always draw a quick, rough sketch before you start. It'll help you plan your steps and not mix up the sum and difference methods. So here it is, your final checklist for a perfect score, your exam day power-ups. Always start with that rough sketch. Use 2 different pencils to make your final shape pop. Leave all your work visible on the page. Label every single point and measurement clearly. And if you have time, just jot down the basic steps. It proves to the examiner that you know exactly what you were doing. And that's a wrap. It's a skill that seems really simple, just lines on paper. But as we saw, it's all based on pure, undeniable logic and proof. You know, this is the exact same kind of thinking that built the pyramids and designed the cities we live in. So the only question left is, what will you build with it? Thanks so much for joining me, and I'll catch you in the next one.